My name is Daniel Logan, and along with my project mates Samuel and Ruben, we will be discussing the machine learning project titled Autoencoder versus PCA for dimensionality reduction and feature learning using Spotify audio features. The main focus of this project was to compare a classical linear dimensionality reduction method, which is principal component analysis PCA, with a neural network based approach, the autoencoder. We applied both methods to real world music data from Spotify in order to evaluate how well each technique compresses high dimensional audio features while at the same time preserving meaningful information. Music streaming platforms like Spotify generate large amounts of numerical data for each song, such as energy, tempo, loudness, and danceability. These features are used in many real-world applications, including music recommendation systems, playlist generation, and song similarity analysis. However, working with many features all at once can really be inefficient, and it may include kind of redundant information, etc. This makes tasks such as analysis, visualization, and model training just so much more difficult. Dimensionality reduction addresses this problem by transforming data into lower dimensional spaces while keeping the most important information at hand. PCA also is one of the most commonly used techniques for this purpose, but is limited to linear relationships, where this is different as opposed to autoencoders. Autoencoders, on the other hand, can learn non-linear representations, which may be better suited for complex data like audio features. This project was motivated by the question of whether the complexity of autoencoders actually leads to better feature representations compared to just a simpler linear method such as PCA. Next is the dataset. The dataset used in this project is the Spotify audio features dataset, which was easily obtained from the site Kaggle. The dataset contains about 130,000 tracks, each described using 13 numerical audio features such as danceability, energy, loudness, and tempo, as mentioned earlier. Only numerical features were used to ensure a fair comparison between these methods. Before applying reduction, all features were standardized to have zero mean and unit variance, since both PCA and autoencoders are sensitive to feature scale. This dataset is well suited for the project because it was large, it's real world, and it also contains numerous continuous features that benefit from dimensionality reduction.
Hello, my name is Samuel Etherington, and I will be talking about the methods we used and the results of our testing. As mentioned by Daniel at the start, the two methods we used for this project were principal component analysis and an autoencoder. Principal component analysis works by projecting data onto directions that capture the maximum variance, thus reducing the dimensionality. It is quick, simple, and easy to interpret. Combining that with the fact that it is also a well-established linear reduction technique, we believe this to be a perfect baseline for comparison. An autoencoder, on the other hand, is a neural network that learns to compress data into a lower dimensional latent space, and then reconstructing it through unsupervised learning. We decided on this for our non-linear technique because the flexibility it provides and the complexity of our dataset. Some of the variables may have non-linear relationships with one another that the autoencoder would be able to capture. For both of these methods, we tested using multiple different sizes of latent dimensions, being 2, 5, and 8. We did this to compare how well the methods preserve information. To properly evaluate the performance of the methods, the reconstruction error was measured using the mean squared error. Through our testing, we found that the autoencoders consistently achieved exceptionally lower error rates compared to the PCA across all latent dimensions. In fact, in some cases, the autoencoder had a mean squared error rate 64 times lower than the PCA. From these results, we can determine that the autoencoders will preserve much more information when compressing things like the audio features found in this dataset. We determined this was likely because the autoencoder could capture nonlinear relationships in the dataset that the PCA could not. We also found that while both methods improve as the latent dimension increases, the improvement for the autoencoder is much more significant than the PCA. On top of all of this, through the visualizations of the reduced feature space, we saw that the autoencoder representations are much more compact and structured than the PCA.
My name is Ruben O'Dwyer, and I'll be going over our key insights for the project and our conclusion. Looking at the results overall, the key pattern is consistency. Across all tested latent dimensions, the autoencoder achieves lower reconstruction error than PCA. While both methods improve as dimensionality increases, the performance gap consistently remains in favor of the autoencoder. This indicates that difference isn't due to specific configuration, but rather a fundamental difference in how the two methods learn representations. The main reason autoencoders outperform PCA lies in their ability to model non-linear relationships. PCA is restricted to linear projections, meaning it can only capture variance along straight directions in feature space. In contrast, autoencoders use neural networks with non-linear activation functions, allowing them to learn more complex interactions between features such as energy, loudness, and tempo. This makes autoencoders particularly well suited to audio data, where relationships between features are unlikely to be purely linear. However, better performance comes with trade-offs. Autoencoders require more computational resources, careful hyperparameter tuning, and longer training times, whereas PCA is fast, deterministic, and easy to interpret. Additionally, reconstruction error measures how well data is preserved, but does not directly evaluate performance on downstream tasks, such as recommendation or genre classification. So while autoencoders perform better in this setting, PCA remains a strong baseline in scenarios where simplicity or interpretability is more important. In conclusion, this project shows that while PCA provides an efficient and interpretable baseline for dimensionality reduction, autoencoders are more effective at learning compact and expressive representations of Spotify audio features. For complex real-world data, such as music audio features, nonlinear feature learning offers a clear advantage. However, the choice between methods ultimately depends on the trade-off between simplicity, interpretability, and performance. Overall, this highlights the importance of selecting dimensionality reduction techniques based on both the data characteristics and the application requirements. Thank you.